Hey everybody, welcome back to chemistry. If I can increase the slide. It reads as follows. Calculate the number of pounds of carbon dioxide released into the atmosphere when a 12-gallon tank of gasoline is burned in an automobile engine. Assume that the gasoline is primarily octane, and then you're given a density for the octane. You're told there that you should assume there are no additives mixed in with the octane, so you should assume that it's pure octane. You should assume that the octane undergoes complete combustion. And then also I'm kind of adding in there what the molar mass of octane and the molar mass of carbon dioxide are. Okay, so can I lower the slide? Okay, so this is kind of a tricky problem. And so what they're trying to have you do is you're given a certain volume of octane. And so one thing you should know is what the formula for octane is, and so it is C8H18. And so you're told that you have 12.0 gallons, and you're going to stick this into a car engine, and it will combust, and it will break down into products, and one of the products that is produced is carbon dioxide, so it's CO2, and you have to figure out how many pounds of carbon dioxide produced from the 12 gallons of octane. So one thing you really have to do to get started on this problem is we need to know what the stoichiometry is between octane and carbon dioxide. In other words, what we need to know is what the coefficients are in front of octane and in front of carbon dioxide. So in order to figure that out, you have to write a balanced equation for this reaction. So this is a little tricky. You sort of have to recognize that this is a combustion reaction. And then you have to remember that in combustion reactions, you take here a hydrocarbon, it reacts with oxygen, and then the products are carbon dioxide and water. And then once you've written out those formulas, then you have to balance the equation. So let me go ahead and do that now. So I'm going to start out with octane here. And it will react with oxygen. And the products you will get are carbon dioxide and water. So I think you can see that this is not a balanced equation. So for example, on the left side right now we have 8 carbons, on the right side we have 1 carbon. So we have to balance the equation. So when you have a combustion reaction, the best thing to do is to first balance carbons and then balance hydrogens. And then once those are balanced, to go back and balance oxygens. Usually that makes it a little bit less complicated. So here we have 8 carbons on the left. We have 1 carbon on the right. So I'm going to put an 8 here. So now we have 8 carbons on the right. Let's balance hydrogens next. We have 18 on the left. We have 2 on the right. So to balance hydrogens. So now let's count oxygens on the product side. And so I'm thinking you can sort of see here that 8 times 2 oxygens is 16 oxygens. And then here we have a total of 9 oxygens. And so on the product side, we have a total of 25 oxygens. You have to think of a number here in front of O2 that when multiplied by 2 gives you 25 oxygens. That'll balance the 25 oxygens over here. So let me just point out this is 25 oxygens. Okay, so what is that number? Well, the number will be 25 halves. So let me explain why 25 halves balance this equation. Again, we have 25 oxygens in the product molecules, and we need 25 oxygens as reactants. And so you can see that 25 times 2 oxygens here divided by 2 is 25. Okay, so sometimes chemists leave the fractions there, other times they don't. And so what I'm going to do is I'm going to rewrite this equation without the fraction. And so the way I do that is I take this whole equation and multiply by what we were dividing the fraction with, which is a 2. So let me multiply the whole thing by 2. So let me rewrite what I have. I'm going to write it up here. 2C8H18 plus 25O2 gives you 16 CO2 plus 18 H2O. Okay, so now we have a balanced equation. So now we can actually make a shot at solving the problem. So let me suggest a strategy for solving this problem. So again, we have 12 gallons of octane and we're trying to figure out pounds of carbon dioxide. So what I suggest you do first is convert gallons of octane to quarts, and then quarts of octane to liters, and then liters of octane to milliliters. And then you actually have a density of octane. So if you have a density of octane, you know the milliliters of octane, you can convert this into grams of octane. So let me again just indicate that this is octane here. Okay, then convert grams of octane to moles of octane. And then once you're in moles of octane, you can use the stoichiometry of the equation to figure out the moles of carbon dioxide. So the next thing would be moles of carbon dioxide, and then from the molar mass of carbon dioxide you can get the grams of carbon dioxide, and then from grams of carbon dioxide, you all remember how many grams there are in a pound? So you have grams of carbon dioxide, you can get this into pounds of carbon dioxide. So what you can see is we're going to start out with 12 gallons of octane, and I'm going to have to write out a pretty long train of fractions to get us into pounds of carbon dioxide, which I'll do right now. Okay, so what I've done is I've started out with 12 gallons of octane, which has the formula C8H18, and I've used 1, 2, 3, 4, 5, 6, 7, 8 fractions to get this into pounds of carbon dioxide. So the answer I got on my calculator was 213.36 pounds, which I think they want the answer in 3 sig figs, which is 213 pounds. So thank you for listening, and we'll see you next time.